Okay, so let's get started. So this is going to be the last lecture before spring break, obviously. But the reason I'm saying this is today's lecture is the last one that is covered for the midterm. Okay, so lectures 1 through 11, which is today's lecture, is going to be on the midterm exam. And anything I talk about the Monday after spring break, which is one day before the midterm, won't be on the midterm, but it's part of the final exam. Okay, so 12 through 24 will be part of the final exam. All right. So today we will start a new topic, but it's the last one in the sequence of talking about processes, threads, scheduling, virtualization. So we'll end that entire group of topics with a discussion of cloud computing. Okay. So we'll have three things in today's class. One of them, just one second. We'll have three topics in today's class. One of them is going to be data centers. You saw some of this when we had a lecture on sustainable computing, but we will now revisit that topic from the perspective of virtualization and cloud. Then I'll talk about cloud computing, and then the last part is actually on cloud orchestration, but that will be a case study on Kubernetes and how you can use Kubernetes to do cloud orchestration. Okay, so three things today. Let's start with data centers. Okay. So what are data centers? So data centers are they're large infrastructure facilities that house lots of servers and storage. Okay. So think of they're called server farm or storage farms. So a facility that has it says thousands, but usually it's tens of thousands of servers, lots and lots of storage, maybe petabytes or more. Okay. They are used by enterprises to house their large server applications. They're used by large internet companies. Any large internet company you already heard of, like Google, Facebook, Amazon. So they all have very large data centers that run their services that you access as an end user. Okay? And they are, of course, used by cloud computing platforms, which is why we are talking about them today. And there are many cloud companies which you might have also heard of. Amazon actually has one of the largest cloud platforms in the world. Microsoft has Azure, and Google has Google Cloud platform. So these are some of the large cloud computing companies. They also run their cloud services on data center. Okay? And these servers can be used for any large task, running large applications, doing data processing, doing machine learning training, which has become a popular use case, hosting web applications of all kinds, business application, anything that you run on servers, you can run on servers that reside in a data center. Right? Here's a small picture of what it actually looks like from the inside. So what the picture you need to have in mind is a large supermarket, okay, where you have aisles and shelves. Okay, and here the shelves actually will have servers, not cereal boxes or anything, any food item. Okay, so it looks exactly the same, where you have this large room, okay, which has lots of air conditioning to cool all of the servers, and there will be aisles. Each aisle will have servers stacked on, so there will be racks of servers. So this is an aisle that you see here, and you see that there are servers on both sides. It's like walking down a supermarket aisle, but you're not buying servers here. This is just hosted servers. So it's a giant warehouse filled with racks of server storage arrays. Okay, so a lot of other stuff has to be put in place to build these data centers in addition to the servers themselves. Okay, so clearly these servers are going to need electricity to power them. So there's a large power infrastructure that is not shown here, but there's a large power infrastructure that is used to power the servers. Okay, and then when the servers are running, they'll generate heat. Okay, so you need actually a very large cooling infrastructure. Think about giant air conditioners that are cooling all of the heat that these servers are producing, and the amount of heat that they're generating actually has kept increasing. Now many of these servers have GPUs in them. Okay, for machine learning type workloads, the GPUs generate even more heat than normal regular servers that only have CPUs in them. So a lot of cooling infrastructure, a lot of power infrastructure, and if your machines are running anything critical, you need backup infrastructure like backup power generators, so that if the power goes out from the electric grid, you can still keep running all your servers. So it's quite expensive to build these data centers, given all of the equipment and the infrastructure that you need to make it all operational. Okay, so that's a picture. But now let's try to think about from a software architecture standpoint, or even some hardware architecture standpoint, what is actually in these data centers. And I'll make a distinction between traditional data centers or data centers as they existed in the 90s and early 2000s, and the data centers, what we'll call the modern data centers, or the ones that exist today. Okay? So in the traditional data centers, things were mostly static. Okay? You had applications that were running on servers, okay? And so they ran directly on physical servers. Okay? And there are storage administrators who had to monitor these servers, they had to physically manage the server. If you wanted to run a new application, you have to then log into the server, install the application, bring it up, and so on. And there was something called storage area network that provided the storage backend for all of these servers. So storage area networks is often called SAN in industry language. And there is something called network attached storage, which provides similar functionality. It's called NAS. Both of these were used to store the data that these servers accessed. Okay? So that was the old view of how to build these data centers. Today, it's the same hardware, but everything is virtualized. Okay? All of these servers will actually run a type 1 hypervisor. Okay? We already talked about what a type 1 hypervisor is. Okay? So these type 1 hypervisors are going to run virtual machines. Okay? So the way you are going to deploy new applications is you'll create a new virtual machine on some server in your data center. And inside that virtual machine, you will have an operating system running, and then the application will run inside the virtual machine. Okay? So everything is now virtualized. So what this allows you to do is there's now a flexible mapping of VMs to physical machines. Last time we were talking about virtual machine migration and live migration. So if some server gets overloaded, okay, you just have to move the VM to another server. Everything just runs without any downtime. We already saw how to do pre-copy and post-copy migration last time. Okay? So you can do live migration of virtual machines, and your load can be rebalanced. Okay? In the old style data center, you can't do that because your applications are running directly on the server. So you can't there's no VM to migrate in that case. So if the machine gets overloaded, you have to shut it down, maybe transfer all the data, transfer the application, start it somewhere else. So all of that gets simplified because the VM can be resized. Okay, you probably have done a lablet where you looked at how to allocate resources. You can resize the VM on the fly by giving it more cores, more memory. You can move it from one machine to the other, and so on. So there's a flexible mapping from virtual to physical resources. This allows automation. Okay? In many cases, the administrator may not actually have to do the migration of our VM themselves. The cloud platform can monitor servers, and if it sees an overload, it can trigger this migration itself to rebalance the load on servers. So a lot of stuff can happen automatically without the user knowing or the system administrator having to take physical actions. Okay? So those are some advantages, but let's now see this in terms of some pictures here. So here is a rack of servers from the picture I showed you. So this is just one of those racks. You will see that there are servers stacked in that rack. Okay? And there is a picture of one server that is shown there. Okay? And that big blue box is essentially your hypervisor, and then you will see VMs. Okay? There are 6 VMs shown there. Each VM is running its own operating system and its own application. Okay? So that's an example of how these servers are actually being used inside a virtualized data center. So these VMs are now called virtual servers because they look like servers to the application and the OS, but they are not actually physical servers. They're just virtual machines that are running on an actual physical server that is shown in the picture. Okay? So virtual servers will give you many advantages. Okay? One of them is called server consolidation. Okay? So what server consolidation means is if you have some number of old servers that are running applications, okay, you can buy a newer server, but a newer server will typically be faster and will have more processing capacity, might have more memory, might have more disk capacity, simply because every time you buy a new machine, it comes with more RAM and more disk and faster processors or more cores and something like that. So you may not need one new server for each old server you are trying to replace. What you can do is, for n old servers, you buy one new server. Okay? You take the old server and all of its application, you virtualize it. Okay? This is also in industry terminology called P2V, okay? Physical to virtual migration. You take a physical server, you take its disk, and you convert that into virtual disk. Okay? And then you can basically run that, whatever was running on that server, inside a virtual machine instead of a physical machine. Okay? So you virtualize the physical server, and you take all of those VMs, and you can maybe put 3, 6, or depending on how large the new server is, you can take multiple VMs constructed from older physical server and put them on a newer server. So now you have the same applications running, but you have fewer physical servers that are needed to run them, because your newer servers became more powerful. Okay? This is called server consolidation. You're consolidating a set of older servers onto a smaller number of physicals or virtualized new servers. Okay? Clearly, when you have virtual machines, you can do faster deployment, because you can deploy a virtual machine image. You can bring it up very quickly without having to do all of the work of doing this on a physical server. Okay? And there are reasons to think about maintenance being easier and so on, because you can move the VM. If the hardware on the physical server breaks, you can move the VM and repair the server. The virtual machine and the application run on a new server somewhere else. Okay? So those are some advantages, but let's look at some more use cases. Okay? So that's server-based application. Okay? Virtual machines that you run in data centers can also run client desktop applications. Okay? So this is what is also referred to as the PC in the cloud. Okay? So what you will have is scenarios where, rather than giving powerful PCs to employees, what many companies do now is they actually give you a powerful virtual machine that is sitting in their data center, that is running your either Windows or whatever your operating system is. Windows is the most common one for this type of environment. Okay? And you get what is called a thin client. It's a less powerful machine. Okay? And what you do is you don't actually do any computation locally. From that thin client, you just connect to the cloud, and you connect to your PC in the cloud, and you run what is called a remote desktop application. Okay? So you can just use that remote desktop and it will just look like you're interacting with a physical PC, because it just shows you the same graphical user interface and so on. Okay? So this is a popular use case where you essentially have desktops running on data centers. You access them within client. Desktop is accessible anywhere. You can go somewhere else, connect to your PC in the cloud from some other location. Everything is still intact as is. Okay? And a lot of applications use this. So if you go to supermarkets, right, so the checkout terminal often is a thin client. It may not be running the full-fledged checkout software and billing software on that machine. Okay? It may actually be connecting to some cloud service, and then essentially just you're interacting with the cloud. So not all supermarkets will do this, of course, but that's an example of using a thin client, so that you don't need to put a powerful PC on every checkout counter in a supermarket, for example. But that's not just the only use case. There are many cases where employee desktops are actually being replaced with thin clients of this sort. Okay? You can even use an iPad in this case and just do all of the work on the iPad, connect to a real PC in the cloud. So your iPad doesn't need to run any real applications. You can just do everything in the cloud. Okay? So that's your second use case of virtualization in data centers: virtual servers and virtual desktops. Okay? All right. So now let's talk a little bit about how these virtualized servers can be used for many different use cases, including migration that I was talking about last time. Okay, so here is an example where you have a virtual server. Okay, that virtualization layer is a type 1 hypervisor, which we talked about many classes ago. Okay, and on the type 1 hypervisor, you are going to, in this case, run two virtual machines. There's going to be a Windows machine and a Linux machine. Okay? And what this physical server has done is it allowed you to slice that server, okay, into smaller virtual servers. So you take a physical server, you partition it into smaller virtual servers, each virtual server is essentially a virtual machine that is taking some fraction of the physical server's resources. Okay? So if you have 16 cores and you have 2 VMs, you can give 8 cores to one VM, another 8 cores to another VM. You can partition the memory and so on. Okay? So essentially, you slice the server into 2 VMs. Okay? Each VM here is running its own OS applications. And what you can do is, so here's an example of those 2 VMs running there. But over time, maybe the workload seen by these VMs might change. Okay? Maybe one VM needs more resources than the other because its applications are essentially more demanding. So you can resize these VMs on the fly. And you can essentially increase the amount of resources allocated. You can say instead of 8 cores, I can give 12 cores to the orange VM and maybe only 4 cores to the blue VM. You can do these kinds of changes, which you would never be able to do on a physical server. You can't actually do this without buying real hardware and putting more RAM or something like that into a physical server. Here you can just resize them on the fly. You can also move them to another machine. Okay, we saw that last time. So here you can see that the Windows machine has needed more VM. So you could potentially just move the other one and then leave the bigger one there. Okay, so that way you gave it more resources instead of overloading it. Okay. There are many type 1 hypervisors that I talked about. Okay, we talked about Zen, we talked about KVM. VMware has many different products that have different types of hypervisor. Popular one is called ES6 hypervisor. And then there are some other smaller companies like Parallels that also do this type of virtualization. Okay. So these are companies that provide these virtualization frameworks largely for cloud platforms. Any questions on this? Okay, you already saw how to do that migration last time, so I'm not going to go into the details of how that migration happened. Okay, yes. Okay, question is how migratable is a GPU as a resource? Okay, so that's a little bit harder problem. Typically, these VMs that are migrating, they don't actually have specialized resources, although that is changing. I'll say this. So these VMs are standard PCs where you have 3 or 4 primary resources: CPU, disk, memory, and a network card. Okay. Of course, there are specialized resources, GPU being a very popular one. Okay. So typically, you can virtualize a GPU. Okay. There's a lot of research on how to take a physical GPU and construct smaller virtual GPUs across them. In fact, the most popular GPU line comes from NVIDIA. Okay. So they actually have a technology on their larger GPUs that is, I think, called MIG. I forget what the acronym means, but it's something that allows you to slice the GPU into up to 7 smaller GPUs, and each GPU can be allocated to an application. Okay? So in that case, you can take a GPU on a physical server, you can then slice it into smaller GPUs and allocate each one to a virtual machine. Okay? Now, when you migrate a VM, you cannot migrate the GPU. You can't migrate the virtual GPU very easily. So you may have to do some extra work to make all of that happen. But having said that, the resource itself is now virtualizable, even though maybe a few years ago that was one of the harder ones that you did not virtualize typically. Oh, thing seems to have crashed here. Hold on. Okay, so yeah, I think that's a new resource that's very popular in cloud platforms. It can be virtualized, although a lot of the GPUs that you can get from cloud platforms that typically may not even be virtualized. You might get the full GPU, which is why cloud servers that have GPUs are still very expensive. The GPUs themselves are very expensive. Okay. Any other questions here? All right. So very quickly, I'm going to talk about data center costs, and then we'll switch to cloud computing. So as I mentioned, your data center is going to have lots of servers, lots of storage, lots of power infrastructure to power this server, and a big cooling infrastructure to cool this data center. Okay? So running a data center is going to be quite expensive because all of these pieces of equipment will consume power, and then you will have to essentially pay a bill at the end of each month based on how much power your data center has consumed. Okay? Now, before we talk anything about power, there is a metric I want you to be aware of, or I want to introduce, that captures how efficient the data center is. And this metric is called power usage effectiveness, or PUE. Okay? So there's a small equation here that tells you what the definition of a PUE is. A PUE is simply the total power consumed by the data center divided by the power consumed by the servers in the data center. Okay? So it's just a ratio. So you can essentially say, let's say that total power, the total electricity bill from a data center is 100. Okay? So that's the total electricity that's consumed by everything, including cooling and whatever else, the network switches and so on. Then you also try to figure out what is the electricity that the servers themselves consume. Maybe that's 70. Okay? Then PUE is going to be 100 over 70. Okay? So it's going to be a ratio that's always greater than 1, because the total power is going to be greater than the power of only the servers, because there will be at least some other equipment in your data center. Okay? The ideal value of PUE is 1. Okay? That means that all the power or the electricity that's going into a data center is going to power the servers, and servers are what are doing the useful work in your data center. Okay? But often you will see that some older data center have PUE of 2. Okay? What that means is for every unit of electricity your server consumes, there's additional unit of electricity that's overhead, that's going into cooling the data center and doing some other things. Okay? So cooling data centers is going to be an expensive proposition, because you have to run these air conditioners, right? That's how you cool them, and air conditioners are going to consume a lot of electricity. So the PUE is often much greater than 1, okay? Closer to 1.8 to 2. Okay? Now, so because that's going to increase your electricity bill, there's been a lot of research done on how to reduce the power usage effectiveness of the data center, or just how to make the data center more energy efficient. Okay? The ideal value is now coming down, and the most efficient data centers that you see today have PUE values of 1.1 or lower. So they are maybe 1.07, 1.1. So what that means is they made the cooling extremely efficient. Okay? In some cases, they actually don't use air conditioners. They put the data centers in cool climates, and then they just bring outside cooler air and just let that air cool the data centers. We just exhaust the hot air and then bring in cool air from the outside. So you don't need to really put an air conditioner to cool it. Okay, but this can only be done if you put your data center in a cold location. If you put it in a warm location, you are not going to be able to use these types of techniques. Okay? So a lot of work on making data centers more efficient, but regardless of how efficient they are, they still cost a lot of money to run, because the servers themselves are going to be quite expensive in terms of their power consumptions and their energy usage. Okay? So you can see here is one example of a typical cost of a data center over a 3-year period. Okay, the blue is here the blue is the servers. Okay, so this blue pie chart is the servers. Okay, you will see that this is a small data center. Over 3 years, it cost $3 million to just power the servers, not buy the servers, just power the servers. That red is essentially cooling, okay? And the green is some other power losses that you might have in the system, or power other equipment in the system. Okay? So millions of dollars can go into powering any data center. So making it efficient is actually going to save you money in the long. Yes, question.
This is like a 1-year running cost of the data center. Does this also include maintenance? The cooling and power infrastructure would require regular maintenance.
Yes. So question is, this is essentially the power cost, and is there any maintenance cost? So these are actually costs include, these are called what are called operational costs, or OPEX, right? So this include not just the power, but other small maintenance costs. Okay? And then there is, of course, the capital cost, which is called CapEx, which is buying the server. Okay? That is not even here. To buy the servers itself cost a lot of money, and then to keep them running costs even more money. Okay? So data centers are expensive to construct and expensive to run, but they are also providing lots of services to users. So hopefully the companies that build them make a lot of money, so they can actually recover the cost of building. Okay? Any other questions here? All right. So with that background, now you know a little bit about what are data centers. Let's talk about cloud computing. Okay. So first thing is, what does the term cloud computing mean? I presume all of you at least heard of this, but I will try to define it and try to understand how cloud platforms work, what they provide, and so on. Okay? So at a very basic level, cloud computing is basically the use of remote servers to run distributed applications. Okay? The servers where you are running your applications are not located on your location or on your premises of your organization. They are somewhere else on the internet that you can access them remotely. Okay? So from, let's say, UMass's perspective, the servers that will run, let's say, Spire or some other application that you may be using, they're not actually based here. They're not running on campus. They may be somewhere else remotely. Okay? So if you have the ability to use remote server to run your application, that at a very basic level gives you cloud computing. Okay? But there are other aspects to cloud computing than just making something remote. It's not like you put a server somewhere remotely, now you have cloud computing. You'll see that there are other aspects. Okay? The other main aspect of cloud computing is you don't own your servers, you actually rent the servers. Okay? So you basically go from an ownership model to a rental or a leasing model. Okay? So it's somebody else's server that you are leasing, and you are just deploying your applications on them. Okay? So that's the other big change. So you are no longer creating your own IT data center. You are just using servers that some other provider gives you, and then you just rent them and run your applications. Okay? So remote servers and servers that essentially you lease to run your application. Okay? So what are the benefits? Benefits are they are remotely accessible from the internet. Okay? So you can access them from any location. Okay? There is a pay-as-you-go model. So you don't actually have to buy a server to run your application. Okay? You can simply lease the server and pay an hourly cost or a daily cost or a monthly cost, depending on your cloud provider's terms on how much it is going to cost you to use that server. Okay? So no need to buy. Okay? You are essentially going to just pay as you go. Okay? It's going to be highly scalable because you can add resources on demand. If your application that's running on the cloud server gets overloaded, you don't have to go buy a new server. You just ask the cloud provider for a bigger server, and you migrate your application to the bigger server. You're done. Okay? You just pay a higher monthly bill, but there's no need to go buy a server or anything like that. In the old days, when you ran servers in your own facility, your machines got overloaded, you literally had to go buy another server, which may take 2 or 3 weeks to arrive, and then you actually add capacity to your application. Here, you can add capacity in minutes, not weeks or days. Okay? So it's much faster to provision resources on demand. It's a shared infrastructure because you are not the only customer the cloud provider has. There are many customers, so they can build these huge data centers and get economies of scale, which means that they can give you a lower cost than you might incur if you build your own data center. Okay? So many benefits of cloud computing. Okay? But from our perspective, we are actually going to look at maybe the top few, which is how do you use them to run distributed applications, and what some of the billing models are to essentially lease these data centers. Right? So let's first start with the cloud stack or different types of cloud platforms as they exist. Okay? There is no such thing as one type of cloud platform. Cloud platforms come in many different flavors. Okay? Here are 3, and I'll talk about one more later on. Okay? So you might have what is called an infrastructure as a service cloud. IaaS is the acronym you will see sometimes. Okay? It just stands for infrastructure as a service. Okay? That's called what's one type of cloud platform. You might have another type of cloud called platform as a service. That's called PaaS. Okay? Platform as a service. That's the acronym that you will see. Okay? Platform as a service cloud. Or you might get what is called a software as a service or a SaaS cloud, SaaS. Okay? So they are all, by and large, allowing you to do what I said on the previous slide. Your servers are remote. You have pay-as-you-go model. You don't buy your servers and things of that sort. But they differ. These 3 will differ in terms of what they are providing to the cloud customer. Okay? If you have infrastructure as a service cloud, you are essentially renting virtual machines. Okay? You are renting virtual servers. And then on that server, you can run whatever you want as the customer of that cloud provider. Okay? So you are paying for basically virtual machine and network access to the virtual machine and network band. So that's what you pay for. Okay. If you are using a platform as a service cloud, you are no longer renting virtual machines. You essentially have code, and then the cloud provider is giving you a platform to deploy that code. Okay. So you basically deploy it on that platform. You don't worry about how many servers are needed or anything like that. You just tell the platform provider, here is essentially my code, and then they will just deploy it, they will run it, and you will just get billed based on how much resources you use. Okay. So you are renting essentially servers plus software that was already deployed by the cloud provider. Okay. And you bring your application. Okay. Here you will bring your operating system and your application, and you're just getting virtual machine. Here you get a virtual machine, OS, and some software, and then you're just running on top of that. So you're essentially just bringing your code. And then when you have software as a service, you essentially get an entire application, and you're just getting access to that application. Okay. So there are many Google Cloud, or not Google Cloud, but Google applications, Gmail and Google Drive. Those are example of software as a service cloud, because you are getting mail service. Okay. You are not getting a virtual machine and you run a mail server. You essentially get mail as a service, and then you just pay by number of user accounts for that service. Okay. That's an example of a software as a service cloud. So Gmail, and there are business applications like Salesforce, Office 365. Okay. That's Microsoft's software as a service offering for their Office application. Okay. So you have Word in the cloud, and Excel in the cloud, and PowerPoint in the cloud, and you have same thing with Google Docs. You can do numbers and sheets and whatnot. Okay. So these are all example of cloud services, but you get the full stack from hardware all the way to application. You just come and use that. Okay. So in different layers, you get different things. So here you got to build everything on your virtual machine. Okay. Cloud provider only gives you a VM. Okay. At the top, you don't have any code of yours running in the cloud. They give you everything. Okay. You just use the application in the cloud as if it's basically running locally. Is this clear? Okay. So IaaS, PaaS, SaaS. Okay. Three types of clouds. We'll talk a little bit about each of these now. Okay. Let's start with IaaS cloud. Okay. The example we are going to use is Amazon. Okay. Amazon's has a very big cloud service. It has a specific one for IaaS cloud, which is called Elastic Compute Cloud, or EC2. Okay. So that's where you go and you essentially get virtual machine. So here is where, if you just want to rent servers and do everything yourself, you go and basically go to EC2 and start a new machine, a new virtual machine, and then you can log in and do whatever you want on that machine. Okay. So this is going to use type 1 hypervisors. It's going to essentially give you a VM. You can deploy your own OS in there. Okay. So, and each physical server could run multiple virtual machines belonging to multiple customers. Each customer gets a login into their virtual machine. They don't see anything else happening on that physical server, but typically there are many other VMs running on that physical servers that belong to others that you don't even know. Okay. So you will have multiplexing of resources on each physical server. Okay. And you can create these VMs almost instantaneously. You can just go to EC2 and request a VM, and it's ready with sometimes in seconds, but often in minutes. Okay. It's ready to go. You can then just log in and use it. Okay. And you will pay based on what type of how large the VM is and what type of VM you provision. So here are three examples. Literally, there are now hundreds of different types of VMs you can rent from Amazon or any cloud provider. Okay. They vary in size in terms of how much memory they have. Users have a GPU or no GPU on your VM. What kind of disk it has? How many cores does it get? All kinds of differences. Okay. So I've just given you three very trivial examples. You will do a cloud lablet at some point after the midterm exam, after spring break, and you will have to use EC2 cloud to actually provision VMs and so on. So you will see this when you try this. But here are three examples. There are three types of offerings of VM. There's a small VM, medium size, and large. A small VM has only one core. Medium one has 5. This one has 33 and a half. Okay, so why it does half, I'm not going to get into, because those are not real servers. They are called elastic compute units, which map to real core. So you can have fractions there, but it's almost like a core. right? You'll see they have different amounts of RAM, but more importantly, you can look at the price to rent these VMs. Okay, the small one is basically pennies every hour. Okay, the large one here is $2 an hour. Okay, so depending on how many hours you run, at the end of the month, you'll get a bill saying you had these many VMs, this VM ran for these hours, the other VM ran for these other hours, and they'll basically charge you based on whatever size VMs you had. Okay? And on top of that, you have to sometimes pay for network bandwidth. Okay? So essentially, any network bandwidth that's coming from outside the cloud, you have to pay for. And in some cases, depending on the type of VM, you might have to pay for storage as well. Okay? If you're using local disk on the VM, you don't pay for it. But if you have what is called elastic block service or elastic file system, which is external storage, you have to pay extra for that VM. Okay? So it should give you some flavor of how much it costs to rent these VMs. But as I said, now there are hundreds of offerings, not just one or two, and in different locations. It's not just I want a VM. You have to basically pick which location you want the VM. Any cloud provider will give you at least 20, 30, sometimes up to 100 different locations across the world. So you got to say, I want it in Washington location, or I want it in some country in Europe or some country in Asia. You can pick where your VM runs. Okay. Any questions on this? All right. So that's your infrastructure as a service cloud. Okay. Next, okay, maybe I'll talk a little bit about some additional details here. So now these sizes of VMs will dictate the price, but also the price will depend on what type of commitment you are willing to make to the cloud provider. Okay. So the simplest type of VM is called on-demand VM. On-demand VMs can be purchased at any time. You can keep them for as long or as little as you want, and then you can terminate them and say, I'm done. And then you're only charged for how much time you had those VMs for. Okay? So there's no commitment of how long you want to keep the VM. You can start them on as you wish and stop them and terminate them whenever you want. They are billed by the second. Okay? So you can get a VM for 3 minutes, you'll be only charged for 3 minutes. Okay? Or you can have them for 3 years, you'll be charged for 3 years. So there's no commitment. Okay? So that's called on-demand. It's provision on the fly. It's not pay by the minute. Now they change to pay by the second. You keep them until terminated. Okay? And then if you are willing to make longer term commitments, you can get discounted rates over on-demand. So something called reserved instances. Reserved instances require you to either have a 1 year or a 3-year contract. Okay? It's almost like cell companies, right? So you can either have a contract for your cell service or you have pay as you go, no contract, right? Same kind of thing here. So there is either, if you make a commitment, you get a discount. Right? So if you make a 3-year commitment, the prices will be 60% of what I showed you on the previous slide was on-demand price. The price is same machine, but you'll get it for less, but you got to keep it for that period because you said I need it for 3 years. You can't just say I'm done with it. Even if you say you're done with it, you'll get charged. So that's what you committed for. Okay, so those are called reserved instances. And then there is something called spot instance. Okay? So spot instances are an interesting case where the cloud often has excess capacity that's not used. And they will essentially build this large data center. It's not assumed that the entire data center is in use all the time. Okay? There will always be idle capacity in the server. So what cloud providers started to do is the idle capacity doesn't bring any money, and no revenues from idle capacity because nobody is using those servers. Okay? So what many cloud providers started to do was saying the idle capacity is often offered as highly discounted rates, okay, to customers. So these are called spot instances. This is excess capacity given at a very high discount. The discount can be as much as 90%. So you are getting the machine for 10% of the on-demand price. Okay? So you might say, what is the catch? Why would I ever buy on-demand if I'm getting the same machine at 10% of the full price? Right? So there is a catch. There are two things. First of all, when you request a spot instance, the cloud provider may say, no, there isn't any that I can give you. Okay? On demand with high probability, if you ask for a machine, you get one. Okay? Because you are paying full price. Okay? Spot, they might say there is too much workload in my data center, I'm not going to give you. So you can get a denial. Okay? That's the first thing. But if you get even if you get one, okay, the cloud providers can actually take it back from you with a warning time. Okay? Normally for on-demand and reserved, okay, you as the customer get to decide how long you want to keep it and then terminate the instance. Okay? For spot instances, because it's excess capacity, these are revocable instances, which means that if there's more demand arrives in the data center, they can take it back from you. They can give you a warning and say, I'm taking it back. Okay? So if you get a spot service, you always have to take a risk that the machine may just be go away. Okay? But you don't get to keep it for as long as you want. If the demand goes up, the machine is taken, which is why you're getting it as a discount. Right? Because it's almost like airline saying, I'll give you a seat for 10% of the price, but there is some chance when you show up at the airport, you may not get on the plane because somebody who's willing to pay more showed up. We gave your seat to that person. Okay? Same thing here. Right? So these instances are good if you want to do large computation at off-peak times when you can get these machines at highly discounted prices, but there's always a chance that your machine will go. Okay? So you got to keep saving your state so that the machine gets terminated. Next time you started, you didn't waste all of the cycles doing something and the machine got terminated. Okay? Any questions on these three things? Yes. Okay, that's a good question. Question is, you will always get a warning. It's not like it's suddenly going to disappear. You'll get a warning, say, your 5 minutes, we're going to take it in 5 minutes. Actually, the warning time is 2 minutes, okay, on Amazon. Okay, so the question is, if you get a warning, can you change it to on-demand? Certainly, what you can do is, if you get a warning, you save your state, then you can go and request an on-demand. You can't change this one to an on-demand. You can't say, you gave me a warning, I'll pay you more. That's not possible. After the warning, the server will be taken away. But you can save all of your state, okay, and then request an on-demand and restart your computation. Okay? Or you wait until the peak workload has subsided, and then you can request it again. So you can just say, I'm not going to pay more. I'll just wait the next time you're willing to give me a spot server. So you can keep requesting until it's granted again. Okay? So one of those two things have to be done.
On their server. Can they give us the on-demand at that time?
Yeah. So question is, if you have a warning, can you get an on-demand at that? That's your question, right? So you have to always request a server. Okay? Cloud provider doesn't give you servers without being requested. So when you get your warning, you can go and say, I need a on-demand server of the same size. Okay, and then if you get that server, and usually on-demand servers you get with higher probability, spot servers lower probability, and they can be taken away. You can certainly get at that time and just move at that point. Okay, so if you have very fast migration capability, you can get the server and even move it before the server shuts down. Okay, but often you may not get it that quickly because a short warning is basically 120 seconds in which you got to save the state, move it, and start somewhere else. But people actually looked at whether you can migrate in that amount of time. Okay. Any other questions? Okay, so these are the three types of instances in the IaaS cloud. Let's now talk about platform as a service cloud. Okay, so as I said, in this case, you're not renting servers. You're essentially renting a platform. What is a platform? You can think of a platform is essentially a software stack that allows you to run applications. One example may be you may get a Python stack, you may get a Java stack. So you essentially bring a jar file and you say run, and then the Java stack and all the OS, everything JVM is already provisioned, and they'll run your Java app. Okay? Or you can bring a web application. Okay? You can have Node.js. Okay? So you can get a Node.js application, they'll run it for you. Okay? You don't have to get a server and install OS, install Node.js, then you run the app. None of that is needed because they have already provisioned all the software needed to run popular applications. So you don't have to do any extra work. Okay? So not only that, as an application provider, you just provide the code. You don't need to worry about how large a server to get. In the previous case, if you want to run an application, you have to decide, do I need the small, medium, or the large one? Or there are extra large and there are 4 extra large. Which size is the right one? You don't know a priori because you may not know how loaded your application is going to be. Maybe it will be very popular and you need a big server. Maybe not so. You might be fine with the medium server. But as the application developer, you have to decide that. Okay? And if you make incorrect decisions, your either application gets overloaded and users will not get service, or you have a big application, big server, and nobody is using it, so you're paying a lot of money, but not getting usage from your server. Here, you don't need to worry about that because you are just saying, here is my application code. Okay? The cloud provider will run it. Okay? They will figure out if the code gets a lot of requests, they will put it on a bigger server. Okay? If not, they'll put it on a smaller server. All of this is done for you by the cloud provider. You get billed based on the number of requests that are getting serviced or something like that, not based on which size servers you got. So they will bill you based on usage, not based on machine size or anything like that. So your job as application developer is simplified because they will auto scale your application for you. They'll make the server bigger, smaller, run it on more instances. All of that is done. So users don't need to provision or manage resources. Billing is not based on time you had the server. In this case, billing is based on workload and usage. Okay? And there are many such platforms. Google's cloud has one called App Engine that supports all kinds of popular platforms, but almost every cloud provider has platform offerings for all popular application stacks. Any application stack that you can think of that is popular, you will find an offering for it. So you don't need to go and provision everything yourself. Okay. All right. So I'm going to give you one example, a modern example of platform as a service. Okay. It's called serverless computing. I don't know if you heard this term. Okay. So serverless computing, it doesn't mean there's no server, unlike the name suggests that there's no server. Serverless computing means you as application provider, developer, don't have to worry about servers. You worry about writing your application. The cloud provider figures out how many servers to give to your app. Okay? It's essentially a platform offering, okay, with some examples that I will talk about in just a second. So developers will deploy code, eliminates the need to provision servers. Same thing what I said last time. Okay? Cloud provider can automatically scale up or down. Okay? It will figure out based on number of requests your application sees, how much resources to give it. Should it put on a bigger VM, smaller VM? They'll figure it out. Okay? And more importantly, if your application sees no requests at all, it's sitting there idle, they'll scale down to 0. Okay? Saying why should they waste resources if the application is sitting idle, nobody is accessing your whatever game that you wrote? Then they'll say no resources. When the first request comes in subsequently, they'll spin it up again on the fly. Okay? So you can go all the way down to 0, which means that you have no VM, so it's not consuming any resources if it's sitting there idle. Okay? So this is basically what the cloud provider will do. You don't need to worry about it. But as the reason I mentioned serverless computing, because it looks like a platform as a service offering, but there is another reason I mentioned. There's a popular way to write serverless computing application, which is called function as a service, or also called FaaS. Okay? So what is function as a service? Function as a service is you take your application, okay, and you write your code as a set of small functions. Okay? And each function is deployed independently, and functions talk to one another. Okay? Now, if you heard of the microservices architecture, which we'll talk about soon, by the way, but your lab 2 requires you to make a microservice. If you haven't read it, go read it. Okay? Microservice architecture says take a big application, make it into smaller components, run each component independently. Okay? That's what microservices. So if you take the microservices architecture to the limit, you are going to get a function as a service where your each component is a very tiny piece of code. Okay? As the name suggests, it can be as simple as one function, but it doesn't have to be a single function. It can be more than a function. So you can think of your code as deploying individual procedures or very tiny services that all talk to one another and build your application. Each service or each function can be scaled up or down independently, depending on how much load it gets. Okay? So what serverless computing does is it forces you as an application developer to architect your application, okay, in a function as a service model. In the platform as a service model, that was not the case. You could write any application you wanted. You could write Python code. You can go deploy it in any way you want. There's no requirement it has to have any certain architecture or anything like that. In serverless computing, you essentially have to write your application as a set of functions, which are, think of it as tiny components. And so these are, each component can be deployed independently. So the platform provider can scale your application in a very fine grain. Okay? It can say these functions get more resources, these other functions are seeing less load, they get less resources, they can scale them up or down. Okay? So they can also, they have other, so functions can be chained together. Often functions are stateless, so they don't have to do I/O. All the state is actually kept and computed and sent back as requests. Okay? And they are more fine-grained than the microservice architecture, which we will talk about. We already saw multi-tier architecture. We haven't seen microservices yet. Okay? But we'll get to that soon. Okay? And in Amazon, there's something called AWS Lambda. Okay? And Lambda is essentially writing Lambda functions, which is how all of this arose. Okay? So you can write these functions. The functions get triggered on the fly when requests come. Okay? You start the code, you execute it, you come back. So you'll see some relation to remote procedure calls. Right? Although these are not RPCs by any stretch of imagination, these are actually web applications that are receiving HTTP requests. Okay? But they're tiny applications. They're individual function-like applications. But they can be invoked remotely like RPCs can, but except that you are accessing them through HTTP. Yes, question? Okay. The question is serverless more efficient than a single server that's busy? Right? That's what you're asking. So the answer to that depends on what the functions are in your application to some degree. Right? So you could write an entire application as single piece of code, one monolithic server. Okay? That's one way to write it. In fact, your lab one did exactly that. Your entire application was one big component. Okay? And then if the component gets overloaded, you have to basically you have to run that piece of code on a bigger server. Okay? Now you can think of, if you rewrote that application using the fast model, essentially each method or set of methods can become one function. Okay? Each of them runs in its own process. Okay? And they communicate with one another. So now if your application is busy, you see which service, which functions are actually consuming more cycles, and only those get scaled up. So from a resource standpoint, this is more resource efficient because you can give resources to individual functions in your code as opposed to the entire code, because not all of those functions may be doing computation. So this is more efficient from the platform provider's perspective. From user's perspective, it doesn't really matter, right? Because you wrote the code now, so long as it runs, you are happy as a developer. Is this clear? Okay. So this is the most modern way people are writing web applications. Okay, is the serverless model. Okay. I will send a paper as part of your reading if you're more interested in knowing more about this. But you will have to know a little bit about how web applications are written to understand. But I gave you the basic idea. Okay. All right. So that's platform as a service. I'll talk a little bit about different cloud models. There are three models here. One is called public cloud, another is called private cloud, third is called hybrid cloud. Okay. So when you go to a third-party cloud provider like Amazon, AWS, Google's cloud platform, Microsoft Azure, Alibaba has its own cloud, and so on, you are using what is called a public cloud. Public cloud essentially says that it's the third-party cloud. The cloud is run by some cloud company. You are essentially creating an account on their service and then getting cloud resources and paying for it. Okay? And all of your code, all of your data resides on somebody else's server, which is the server of the cloud provider. Okay? This model is referred to as a public cloud. Okay? Now, not all companies are comfortable putting their data on somebody else's machine, okay? Especially if there is sensitive private information. Think of a banking application, or think of a hospital where you have your private medical data, or banks have financial information. You put it on somebody else's servers. If the servers have any security attacks, then your data is essentially got compromised. Okay? So what many companies have done is they have built their own cloud service within their organization. Okay? So they build their own data center. Okay? Data center provides the same service as a public cloud, and that cloud is only open to the employees of that company. You can go and get a virtual machine from your private cloud. This is called a private cloud, and it will look the same. Right? From your perspective, it's like going to some service and asking for a virtual machine, or you can deploy your application and so on. Okay? So in this case, your company that deployed this private cloud controls everything because it is their machines, is their storage, and their applications. Okay? So it's not accessible to anyone outside. So it is used in environments where maybe you do not want to put your data on third-party services. There are often regulatory concerns that say you can't even put data on some outside servers and things of that sort. For example, here at UMass, we can't put student data arbitrarily on some cloud because of FERPA. Okay, we are not allowed to do that. So we have to keep it on our servers, or if you need a cloud, then we have to put our own private cloud and put it in there. Okay? So those are reasons why you might build your own cloud as opposed to going to Amazon or Microsoft and using their cloud service. But beyond that, the cloud that you build can provide the same service. It could be infrastructure cloud, it could be platform cloud, software cloud. All that is the same. Okay? It is just that you built everything as an organization for your employees. Okay? Cost may be a little higher because you are not going to get the economies of scale that these giant cloud companies have. They are called hyperscalers because they have gigantic cloud platforms. So they can build very large systems and get economies of scale. If you build a smaller cloud, your per server cost is going to be higher. Okay? So that's your private cloud. And the third one is called hybrid cloud. As the name suggests here, you are using some combination of a private cloud resource and a public cloud resource. Okay? If you have this, you have got essentially what is referred to as a hybrid cloud. So you may say, why, if you have a private cloud already, why do you need a public cloud on top of that? Right? And the reasons are the same as what I was talking about earlier. So you build a private cloud. It has certain capacity. You put 1,000 servers in your private cloud, say. Right? And you built it. Now users are using it. Maybe there are lots of requests for virtual machines come in. You run out of physical servers to create a VM. Okay? Now you have one of two options. If some employee says, I need a VM, you say, no, machines are all in use, can't give you a VM. That's one option. Second is you can go internally, the private cloud can go and get a public cloud resource, create a VM there and hand it to the employee saying, we are temporarily full, but I'm going to give you a VM on the public cloud. Okay? And that, so you're essentially using combination of resources in your private cloud and your public cloud to meet your overall demand. Whenever you exceed your private cloud capacity, you overflow into a public cloud. Okay? Whenever your capacity has reduced, you can bring your machines back. So you can essentially migrate machines in and out depending on how much capacity you need and so on. Okay? So this requires you to move resources between a private and a public cloud depending on load. Okay? So in some sense, you get the benefits of a private cloud when you can accommodate your applications locally, but you can also use public cloud resources when not. Okay? Yes, questions? Yeah, so question is, how do public cloud companies manage security problems where there are security risks that expose data? So that is a big problem for any public cloud company, right? You are not going to be, you're going to get into trouble with your customer if you expose your data to some other customer, or worse, to some third parties that hacked into your cloud platform and started accessing it. So they try to put in a lot of security rules to do this, but you have to realize you don't have any control as a cloud customer. You're depending on them to implement good security policy. And if their security policies fail, you are actually going to get exposed, which is why some companies will never put their most sensitive data on the public cloud because they want more control. They wouldn't want to say, we gave it to some other company and they got compromised and we are now essentially having to deal with all the issues that come out of that. Right? So yes, I think it's a problem. It's ongoing issues. Every time there is some problem that they have to go figure this out. Any other questions here? Okay, so we have maybe some little bit of time. So let's talk a little bit about cloud workloads, and then we still have to talk about Kubernetes and cloud orchestration. So many types of workloads you can be run on these clouds. Okay, so typical things you run are web applications. You can put your web application on the cloud, and I think at the end of the course in lab 3, you might actually have you deploy some applications on cloud, just so that you get some sense of what you can do there. So those are interactive applications. So you're putting web applications, databases, and so on. You can also put batch applications. These are data processing applications that run in the background. They can do things like payroll and things of that sort. You can put data intensive applications like Spark that take very large data sets, process them. Okay? Cloud is good for this. If you have a job that needs 1,000 servers or only needs them for 10 hours, okay, rather than buying 10,000 servers and only using them for a small amount of time, you can just go to the cloud, get those servers, run, then terminate them and only pay for 10 hours. Okay? So it's much more cost effective sometimes when you have very large needs for short amounts of time. Okay? So that data processing analytics, the big use case these days is machine learning training, which is exactly that. You have a large data set, you want to train a model. Okay? You can go get some GPU servers in the cloud, train your model. Once it's done, release the servers. So you'll just pay for that many hours. Okay? These machines are not cheap. GPU servers cost money, but it's still more cost effective than buying lots of GPUs and then just running your training for shorter periods of time. Okay? If you have lots of demand, then you should provision your own servers. And then there's high performance computing, which requires you to run parallel applications. So all kinds of workloads run on these cloud services these days. Right? Everything from interactive to bash to ML training. Okay? Now, I had not talked much about storage, but there is also storage clouds. Okay? So every cloud provider, of course, gives you storage as well, but there are many cloud providers that only do storage. Okay? Dropbox is a good example. That is a cloud provider that specializes in providing storage. You can put your files in the cloud. Okay? Of course, all other cloud providers do the same thing. Google Drive is an example of storage service that Google provides. Okay? So you can keep your files in the cloud. Microsoft has OneDrive and so on and so on. Okay? Now, within storage cloud, there are actually different models that you can use. Okay? There is essentially, the two most important ones are essentially you can have something called an object storage or file storage. Okay? When you go to Dropbox or you go to Google Drive, you are actually storing files in the cloud. You can take a file, upload it to Google Drive or Dropbox, and you have that file. It just looks like a remote file server for you. But there's another type of storage cloud. It's called object storage, where you get big blobs of storage, okay? And you can put data in that blob using what are called get and put operation. So you no longer put actual files. You can put arbitrary types of data into that blob. This is called object storage. It's used for many reasons like archival storage and things of that. Amazon has a service called S3, Simple Storage Service, okay, which you are going to use again as part of your cloud lablet, where you'll see what object storage is. It's a little bit different from creating files in the cloud. You create these buckets. In that bucket, you can put whatever data you want. The data could be a file. It could be a large archive of something. It could be a database. And then you can get it back using get operation. So instead of read and write, you're going to use get and put operation. Okay, so that's object storage in the cloud. There's file storage in the cloud. You can, of course, have block storage, which is local storage in the cloud and so on. Okay? And so there are many use cases, again, for storage services. You can use backups. Backups is a use case. You can create a backup of your machine in the cloud. You can use it to keep all your other files. You can, of course, keep your email in the cloud and so on. So Dropbox, Google Drive, OneDrive, Box, all of these are examples of storage clouds or this cloud storage providers. Okay, so with that, I'm going to start talking about cloud orchestration in the 10 or so minutes that we have. Okay? So what does cloud orchestration mean? The first thing is what orchestration here means is when a cloud provider receives a request for a virtual machine. Okay, now we are talking about infrastructure as a service cloud. A cloud provider gets a request saying, I want, customer says, I want a large VM. Okay? Now you have to think about which physical server are you going to put that VM. Okay, because you might have a large number of servers, many of them have idle capacity. You might have to decide which VM to put on what machines and so on. This problem is called cloud orchestration. Okay? So you're trying to essentially take your physical servers and then you're sharing them across customers, and then you are putting customer VMs on different servers and mixing them up across servers or multiplexing them across servers. So to do cloud orchestration, you essentially need a cloud controller. So the cloud controller, or the control plane, as it is often called, makes the decision for whenever new requests come in, which machine to put that VM on, how to slice that machine across multiple customers, how to configure the networking, how to boot that VM using a specified operating system. All of this is done by this cloud controller. And so this is essentially a important part of your cloud platform. Users are not actually going to see this. They are simply going to make requests. The cloud controller is going to process the request, come back with the answer, and then you just get your VM. But that logic that's going to do all of that is called your control plane, and this process is called orchestration. Now, with that background, we are going to look at a very popular orchestration platform, which is called Kubernetes. Kubernetes is essentially designed for container orchestration. It's not orchestrating VMs. The cloud control plane actually orchestrates virtual machine. Kubernetes does the same thing on a cluster, but it orchestrates containers. So you can say, I need to deploy this application in a container, and then the Kubernetes control plane is going to say, I'm going to put it on server 7, and it's going to get these many resources and so on. So it is essentially a container-based orchestration system, and it grew directly out of Google's Borg scheduler, which we saw a few lectures back. I remember I said Borg is the scheduler that manages Google's data centers. You will see a direct parallel between what Borg does and what Kubernetes does. So in fact, this Kubernetes came out of Google, and it's essentially the open source version that took some of the features of Borg and then made it available to everyone. So in the world of Kubernetes, applications are containerized. You can make them Docker images. You can make them any other type of container images. You go to Kubernetes, say, okay, deploy this application. It's going to essentially deploy it on a set of machines. And the assumption is application is not one container. It could be a set of containers. If you have microservices, you will have your applications in different container. Each of them is a component of your application. So you might have to deploy n containers all at once. Which machine should have them? Should containers be on the same machine, different machine? All of that you can do using containers. And not only that, Kubernetes can also replicate some of your containers. So if container fails, it will automatically send your request to the replica. It may actually look for failed container, restart them on another container. It will do load balancing. It can do all kinds of things like scale them up or down. So many different services are provided by Kubernetes. Here we are only going to talk about how do you place an application on a machine using a container, and then how is that application getting service from outside. But there are many other aspects of Kubernetes I'm going to gloss over today. But with that background, let's look at some sort of components of Kubernetes. So the first abstraction you need to know of is Kubernetes manages server resources using something called pods. A pod is essentially a slice of the server. But it's not a virtual machine, which is also a slice of the server. You can literally take the server and say, I am going to take 2 cores, 2 GB of RAM, and I'm going to call that slice a pod. On that pod, I'm going to deploy containers. Instead of deploying VMs, I'm going to deploy containers. So pod is essentially a logical abstraction, not a physical thing. The logical abstraction that says it's some slice of a full application. Now it will also have some number of 1 or more containers. It also has its own namespace. It has a name that you can give it and so on. Now, if you think of a distributed application, it has multiple components. Each component runs inside a container, and each of those containers can be in their own pods, or you can share them. So here's an example. of host A, that's a machine. It has one pod. It can have more than one. This one has only one pod, and this pod has two containers. Okay? This pod gets its own IP address, okay, which is distinct from the IP address of the physical machine. So it looks like a VM, but it's not really a VM. Okay? Because VMs also have their own IP addresses. So the pod gets its own IP. So all these two containers can be essentially addressed through that IP address. So they have their own namespace. Okay? So you deploy a container, you get your own private IP address, or it could even be a public IP address. Okay? So a pod can contain all the containers of an application, but typically what you would like to do is each component gets its own pod. So you can independently scale it up or down. Just as in function as a service, I said you can scale up an individual function. So the right model, okay, is not to put two different parts of your application in one pod. You put one component of your application in a pod, and then you can have another pod on another machine, so your application component gets replicated. Okay? And if one goes down, you can then send your request to the other. You can scale them up. If they need more, you can give them more resources. So all of those things can be done. Okay? So an application will consist of a set of pods. Each of those pods will contain containers. Each of those containers will contain parts of your application. Okay? So that's essentially the mapping. Okay? And so you can have your application as a whole span multiple pods. Any questions on this? Okay. So here is now another abstraction. So pod is one abstraction. Pods essentially are a way you are going to deploy containers. Okay? Another abstraction is called a Kubernetes service. Okay? A service is how you take pods and expose it to external users. Okay? Think of a service as being similar to a load balancer. Okay? So you have pods here, and there's a service. The service gets an IP address that you expose to the outside world. Okay? Pods have their internal IP addresses that I showed you in the previous slide. Those are not exposed to the outside. Okay? Requests come to services, and services, or a service rather, for an application, the service will then forward it to the right pod and the right container for processing. Okay? A service is essentially a way you're going to expose your application to the outside world. It will get a static IP address. Okay? Services are not ephemeral, which means that they're going to be persistent. Okay? But pods could be ephemeral. You can essentially take this pod here and then move it to some other machine, or you can terminate the pod, you can scale it up or down, and so on. But the service will then essentially know what's happening to pods, and it will send requests to wherever the pod is. Okay? So one way to think about it, it's a logical abstraction that looks similar to a load balancer. Okay? But there may be no load balance. If there's only one pod, it's simply forwarding requests, not balancing. But as more pods are replicated, it will actually load balance as well. Okay? So this is how you are going to build a Kubernetes web application. You'll take your code, containerize it, okay? Deploy them as pods on Kubernetes, and make a service that knows about these pods, and then the service is exposed to the outside world. So users are only seeing the service IP address. So they are sending requests to the service, and the service is essentially forwarding them to whatever you want. So, and you can see here, there's an example here. So there are different types of pods are created. Some are development environments, some are production environments. So you can have multiple pods. So you can develop new versions of your code, try to test them in the same environment, then essentially make them live, but making them into production, and terminate an older pod and a new version of the service gets deployed, and so on. Okay? So this is highly used in essentially web application world. Okay? This is how you're deploying services, you're doing development of new services and things of that. Okay. I have one more slide here, then we will end it quickly here. Okay, so this is the control plane of Kubernetes. Okay, so it has many different components that are roughly similar to what Borg has. Okay? So it has an API server, okay, which exposes a web interface that Kubernetes provides. So you can essentially talk to Kubernetes saying, create a new pod. Okay, there's a web request you can send to create a new pod. You can say terminate a pod, deploy an application. All of that is handled by this API server. Okay? And then there is another component called etcd that is a key value store that's similar to the Borg master. Okay? This is where the entire state of your cluster is kept, saying which pods are running, which machines are they running on, how many applications or how many resources are you given to applications. So all of that is stored here. Okay. This component has to be replicated, because if that fails, your entire cluster manager will fail, because it will not know what is running where. So just as in Borg, which was that Borg master is replicated 5 times, this is going to be replicated, and it uses a raft consensus, which we'll talk about later, that uses Paxos to ensure they're all consistent with one another and so on. Okay. Then there's a controller manager that replicates pods, manages them for failure, and so on. There's a scheduler that assigns new pods to server. So this is the one that's figuring out if you want to create a new application, which server needs to be used for it, and so on. Okay. And then there's another one that is used for Kubernetes to interact with cloud managers and so on. Okay. So many different components. From our perspective, only 2 or 3 are important. Scheduler decides where do your applications run. Okay. Controller says once the application is running, if there are failures and so on, so restart that pod somewhere else. So it's actually giving you some nice services. And etcd is storing the state of your cluster on disk in a database. It's a key value database, but still a database. Okay. So these are essentially a component of Kubernetes. Again, there is a Kubernetes lablet, which is going to come well after Spring Break. You can play with some of these components to deploy applications. Okay. Just as your Docker that allows you to deploy this, Kubernetes allows you to deploy this in a containers in a cluster environment. Okay. Any last questions on this? We are a minute over. We'll end it here. Okay. So let's stop here. We are done as far as the material for the midterm is concerned. Okay. So everything from first lecture to today's lecture is going to be on the midterm. Okay. So whatever I do after Spring Break, only on the final. Midterm exam, just as a reminder, you've probably seen this, is Tuesday after Spring Break. Okay. It's an evening exam. I already posted the room number. It's not going to be here. Okay. It's going to be another room. I already posted the building and the room number on the web page. I'm going to send that out in an email so that you can have it handy. Okay. I will have extra office hours also after the exam on Monday before the exam and this Wednesday. Okay. So if you have any questions about the midterm or any material is not clear, either come this week before midterm, before Spring Break, not before midterm. Okay, or come on Monday. That's one day before the midterm. So those are 2 office hours you can come talk to me. Okay, so that's it for today. We will have another class on Wednesday, and then we'll break for Spring Break.